we're going to start a whole new section. What we have been doing before is we've been doing questions where we've been given like a whole set of numbers that describe one thing, like for example, the temperature outside or how tall you are, or something like that. And we've been asked to calculate things out of it or graph it or do something like that, okay? We're going to stray away from that sort of thinking. And we're going to start talking about something called bivariate data. Okay, bivariate. And it's literally what the word kind of represents. Bi meaning two, right? We have two variables. Okay, so whenever we're talking about this type of data, we're talking about not just having one list of numbers, but we have data that can be represented using two numbers. Okay, so we have two variables going on. Okay, now the best way I can kind of think of this is by using an example. And one example that kind of comes to mind is temperature and heating bill. Okay, sometimes we have data where we're not just interested in the temperature outside or just someone's heating bill, but the combination between the two and how they might be related. Okay, so for example, let's say we have someone, I can't spell temperature, oh my gosh. Let's say we have someone who lives in an area where the average temperature is like 20 degrees Fahrenheit, so like really, really cold, okay? What would you expect the heating bill to be, high or low? High, right? Because it'd be really cold outside, you want to turn up the heating bill. So let's say the heating bill is like 160 degrees, okay? Or sorry, $160. Okay, well, I can plot that on this graph where the x-axis is the temperature, so 20, and the heating bill is 160. I can plot a point here that represents that data. Okay. On the other hand, what if the temperature was, I don't know, 140 degrees outside? It's pretty hot, right? The heating bill would probably be pretty low, right? So heating bill would be, I don't know, like 20, something like that. Okay, so I'd expect something like this. And I think what we're realizing is there's some sort of relationship between the temperature outside and how high or low your heating bill is. And that's kind of where the idea of correlation comes, okay? Now, if I were to draw even more data points, I would expect my graph to kind of go down as I read it from left to right. So I would expect, okay, maybe in the middle, I'd have an average heating bill, really cold, high heating bill, and really warm, a low heating bill, okay? Now, what I just drew here is called a scatter plot because the points are scattered on the plot, right? And every single dot here represents one data point, okay? Each data point has an X value and a Y value, right? It has a temperature and a heating bill, okay? Now I know this is kind of overkill, but let's just say like the X value was 2 and the Y value was 3. We could represent this data point as what we call an ordered pair, okay? And what this is we just take the two numbers, write them next to each other, and put them in parentheses, okay? You can do the rest, but I think we all know that 3, 6, 4, 10 would also be an ordered pair. So instead of drawing the point on a graph, we can write the point as an ordered pair. Okay. Any questions so far? I think we're all good. Okay. We have bivariate data, which means two variables. Since we have these types of variables and we can plot them on a graph and see how they relate to each other, there's this thing called correlation, which we are going to be talking a lot about today, okay? Now, there's three types of correlation. The first is what we call a positive correlation, okay? Now, the way I like to look at positive correlation is, let's just say our one variable, let's just call it X. Let's say we increase that one variable. So we increase the temperature, for example. If X and Y have a positive correlation, would you expect Y to also go up or to go down? Go up, right? So positive correlation just means that as we increase one variable or as we do something to one variable, the other variable does the same thing, okay? Now, I'll give some examples of things that have positive correlation. Usually height and weight have a positive correlation. For example, if you have a dog that's really, really tall, you would expect it to be kind of heavy, right? Okay. Another one that I wrote down, which I don't know why I wrote this one, but the amount of food that you eat, so food eaten and happiness. Right? If I eat more food, I'm going to be more happy. And if I eat less food, I'm not going to be as happy. Okay. All right, so let's talk about the other type of correlation, which is the negative correlation. If two variables have a negative correlation, well, if I increase the x value, what's happening to the y value? Decreasing, right? And on the other hand, if I decrease the x value, the y value is going to increase. So they do kind of the opposite of each other, okay? Examples of negative correlation would be, how about the amount of time you work? So time worked and the amount of free time you have, right? Amount of free time. So if you increase the amount of time you work, you're not going to have as much free time. Okay. Now, on the other hand, we might not have any correlation. So there is a possibility that two variables don't have any relationship between each other. They kind of, one thing doesn't really imply the other. Okay. We call that no correlation. Okay. So let's take a look at some graphs that have correlations associated with them. The one on the left definitely has a positive correlation because it's going up. Okay, so this one has a positive correlation. Okay, and the way I'm going to write this, and I know it sounds weird right now, but we'll talk about it later, is I'm actually going to measure the correlation. Okay, and I'm going to use this variable r, and r is going to measure how closely these two are related. Okay, I'm going to say that r is close to 1. Because this has a positive correlation and it looks like it's going up pretty strong, I'm going to say that r here is pretty close to 1. Okay. All right. This graph has a negative correlation, right? Because it's going down. And I'm going to use r again. But since the graph is going down, I'm going to say that r here is close to -1. Okay. So I have this variable r that measures how closely these two are related. When it's going up and it looks like it's really going up, r is close to 1. When it's going down, almost like a straight line going down, I'm going to say that r is close to -1. Okay. Now the graph on the bottom, it might look like it's going down, but honestly, I don't think it has any correlation, right? It looks like the graphs are kind of scattered all over the place. So I'm going to say this has no correlation. Okay. And where do you think r is going to be close to here? 0, right? So whenever there's no correlation, I'm going to say that r is about 0. Okay. R is about 0. So we have graphs, we can kind of figure out, okay, what's the positive, negative, no correlation, which one is it? And we can also use r to kind of quantify how much this is. Okay. Before we talk more about r, I just want to talk about another way I might represent these variables that I don't really use that often. Sometimes instead of saying the x variable, I'll say the independent variable. Sometimes instead of saying the y variable, I'm going to say the dependent variable. Okay, so if you hear me say that, that's all I need. Okay, the variable r that I just talked about actually has a name. It's called the correlation coefficient. Okay, and this variable literally measures how closely related two variables are. Okay, the thing about this variable is it can only be between -1 and +1. It can't be anything that is bigger than 1 or less than -1. Okay. And we can kind of look at the value of r to see what the graph looks like. So if r is positive, the graph's going up, and if it's negative, the graph is going down. Let's take a look at some of these scatter plots here. Okay, so for example, scatter plot 1. R here is -0.996. That's really, really close to -1. Now, if you look at this graph, it almost looks like the points are really close to a line going straight down, right? Okay. Now, if we switch our gaze to scatter plot 2, the correlation coefficient is still negative. It's -0.6. The graph is definitely going down, right? It looks like the points are going kind of straight down here, but it's not as close to a straight line going down, right? It kind of looks a little bit more scattered than scatter plot one. So we can have two graphs with negative correlations that have different looks to them. And the difference is that, okay, R here on the left is really close to -1. R on the right is not as close, but it's still negative. Okay. Now, I know the question you're going to ask me is, are you going to ask me to figure out, okay, like what's the difference between -0.6 and -0.9? My answer is no. Okay. The one thing I do want you to know is, for example, if I gave you scatterplot 1, scatterplot 3, and scatterplot 6, I would want you to tell me which one is R equals 0.9. Okay. So you would know, okay, it's definitely not negative, definitely not the one in the middle. It's got to be this one. Okay. Any questions on these scatter plots? Okay, I think it's pretty easy to figure out, okay, which one's positive, which one's negative, which one's close to 0. Okay. Now, along with correlation and our value R, we have this thing that we call the line of best fit. Okay. Another word that we use to describe this line is the least squares regression line. And these lines kind of pop up when you have a scatter plot and you see a line drawn on top. Okay. Now, this isn't just any line that we draw on top of this. It's actually calculated using a bunch of different calculations that I don't think is very useful to know how to do. And we actually have programs to create these lines as well. Okay, so basically what you need to know is when you're given these problems, I'm going to give you this equation of a line of best fit. And you're going to know that if you plot it on top of the points, it's going to kind of fit the correlation of the graph. Okay, it's going to go up if the points are going up. It's going to go down if the points are going down. Okay, we'll come back to this. But before we go to this line, I want to talk about just lines in general. Okay, so if we flip to our next page, let's just talk about lines and how they come about into graphs. Okay. Now, in this example, I have a graph, or I have a line y equals -3x plus 2. Okay. And I'm going to call this line a linear line. Okay. Does anyone know what's special about a linear line? What makes it different than like a quadratic line? It continues, but other lines do continue. That's actually really good, but maybe in more general terms, it's a straight line. Good. So linear just means straight. Okay, so it doesn't curve or anything like that. And linear lines have a specific form. Okay, and you might have heard this before, but it has the form y equals mx plus b. So whenever you see an equation that looks like this, it's a linear line. Okay, let's just say we wanted to graph it. There's two pieces of information we need to graph a linear line, and that's its slope and its y-intercept. You might have heard this before. Let's go over how to get these values. Anyone want to tell me the slope of the line? Claire? -3, good. Okay, so in general, the slope of a line is the number attached to the x, okay? Oh, bless you. Okay, so you're gonna take a look at x, you're gonna look at the number attached to it, that number is the slope, okay? Now, one thing I won't take for an answer of the slope is make sure you don't write -3x as your slope. Okay, that's not the slope of the line, that's -3x, okay? -3 is the slope, okay. All right, what's the y-intercept? 0, 2, actually that's really good. So 0, 2, I would also just take 2, but 0, 2 is really good. The y-intercept is the number by itself, right? The number by itself. Okay. So let's just go about trying to draw this line. I have a little graph for you. And let me just set this up. So it doesn't have to be perfect, but here we have an X and Y axis, okay? And let's just make every block 1. I think we have enough space to do that. Okay. All right, so when we draw when we draw a graph, the first thing we want to do is plot the y-intercept, because that's going to be a point on our graph. If you're ever confused as to what the y-intercept means, just take a look at the name, right? It's the y-intercept, so it's where the graph intercepts the y-axis, right? So since it's 2, I know that on the y-axis, the graph has to pass through 2. Okay, so that's what the name says. The graph passes through 2 on the y-axis. A little bit harder is talking about the slope, right? Anyone know the layman's term of like how to say what slope means? Good, rise over run. Okay, the slope expressed as a fraction tells you how much you need to rise and how much you need to run. So how much you need to go up and down, how much you need to go from side to side. Okay, unfortunately, my slope is just a number, but we can always represent a number as a fraction by putting it over 1, right? So -3 is technically -3 over 1. Okay, so let's just take a look at how this goes in my graph. If I start at 2 and I need to rise -3, am I going up 3 or down 3? Down 3. So 1, 2, 3. And if I'm running 1, am I going to the right or to the left? To the right. Good. So I land right here. This is my new point. Okay. Now this is actually enough to draw the line. Let me just talk about one thing. For example, I wrote the -3 up top. I can move that decimal. Oh my gosh, I could put the negative sign in the denominator if I wanted to, right? Let's see how that would change how I would draw this graph. Okay. I still start at 2. If I rise 3, am I going up or down 3? Up, 1, 2, 3. If I run -1, am I going to the left? Good. So I would end up here. Whichever way you want to go, you're still drawing the same line. You're just drawing a different point on the line. Okay. So let me just connect these dots here. And let's see how good I am at doing this. Oh, that's bad. Let's try that again. Good enough. All right. So once you have 2 points on your graph, you can connect the 2 points, draw your straight line, and that's all you have to do. You don't have to, but I guess that's a good touch. Yeah. All right. Good question. Any other questions? All right. If you flip over to example number 2, we have another example of a graph. I'll give you a few minutes to work on this one here. Are we all good that the slope is 4 and the y-intercept's -5? Good. Savannah, do you kind of want to walk us through how you made the graph?
So I just made the graph, numbered it and everything, and I knew that I know how to start with the y-intercept, just to start from there. So I start with the y-intercept, and it was -5, and then I go up 4 over 1. That's the slope, and then just keep doing that.
Great job. Nice job, Savannah. Any questions on how we got the line here? All right, I think we're all good on graphing lines, figuring out how the line translates into a picture. Let's actually talk about how to create predictions and answer word problems involving these lines now, okay? So let's take a look at example number 3, okay? Big word problem. I am not the best fan of word problems, so I'll talk with you of how to translate this into a regular type of problem. But let's just read this out. We have a group of students. They think that the age and days of a tadpole and how long a tadpole's tail is are correlated. Okay? And I put in the question that the age I'm going to say is X and the length of the tail is 1. They did a bunch of data collection and they figured out that the line of best fit is -1.5x plus 4. Okay. Okay. This question is asking us to predict the tail length of a tadpole who is 2 days old. Now, when I read this, I get flustered when I see word problems, I'm gonna be honest. So what I like to do is to turn this into a regular like X and Y problem, okay? And the way I do it is I'm just gonna write X equals and Y equals on the side just to organize my information. Okay. It says that the tail length, we want to find the tail length of a tadpole who's 2 days old. What does 2 represent, X or Y? X, right? Because in the question, it says that X is the age in days of a tadpole. If it's 2 days, that's an age, right? So we know that X is 2. Now, the question is asking us to find something, so Y has to be the thing we're trying to find. Okay, so I have my equation. Let's just plug in 2 for X. So we have -1.5 times 2 plus 4. Okay. My best advice is to do the multiplication in your calculator first and then add the 4. So I'm gonna do the multiplication first and get, I think, -3. Then I'm gonna write that down and add the 4. So -3 plus 4 is 1. I want, gosh, I would think that the tail length is 1 inch here. Any questions on how I got part of it? Okay, let's do something slightly harder. How old do you think the tadpole will be if the tail is 2 inches long? So same setup. What does 2 represent now? Y, good, because Y represents how long the tail is. So it says the tail is 2 inches. We know that Y is 2. That means we have to find X, right? Okay, let's plug in Y. So we have 2 equals -1.5x plus 4. Okay. This one's a little bit harder because we're not just plugging something in, we actually have to do some solving, right? My best advice to you is to look at this and be like, okay, the 1.5x is the hardest part of this, right? Adding and subtracting is easier than multiplication. Let's isolate the 1.5x first, and then we can do stuff to get x by itself. So what do you think we should do on both sides of the equation? Subtract 4, good. And whenever we do something on one side, we have to do it on the other, right? So on the left, I think I have -2. And on the right, I have -1.5x. Okay. How do I undo multiplication? Divide, right? The opposite of multiplication is division. So to get rid of the 1.5, I need to divide by -1.5. Okay. So on the left, I have, I think, 1.333. Good. And on the right, I have x. I know that I expect the tadpole to be 1.3 days old. Okay. Any questions on what I've done here? All right. Try example 4. I'm going to give you a few minutes to work on this. If you're ever confused about what to plug in, write out the X and the Y and see which one goes in which spot. All right. Looks good as I've been walking around. Let's go through example 4 real quick. This one we have the time required to download a file, and I put Y first, and it said depends on the internet speed, which is X. I gave you the line of best fit, and Jules, I asked you to write up part A, right? Do you want to take us through your steps here?
Yeah. So I realized first I messed it up, but then I realized when I read the problem that the speed was going to go for X. So I put 5 in for X and multiply 2 times 5, got 10.
Great job. Any questions for part A? All right. The main thing I think I see students kind of getting confused about is like, okay, what do I plug in? Do I plug in 5 for X or 5 for Y? If you're ever confused, just write the X and Y on the side, and I promise you it helps a little bit. It definitely helps me. All right, part B asked us if it takes 45 seconds to download a file, what would I predict the internet speed to be? Amari, do you want to take us through this one?
Yeah. So for this one, we got all together, and then 35 from both sides. And 10 by 2
Great job. All right, so this one, we actually had to solve this one. Okay. Any questions on example 4? All right, do we feel good with solving equations? All right, now I keep overestimating the time it takes to get things done. I don't have anything else for you guys, so I guess I'll let you out early.